Hey guys, welcome back to another episode of the Weekly Coder. I am Chris, and today we are continuing on with our Pong Clone tutorial. We are on part 4, and that means we are going to be adding some more advanced ball movement. So, as you're well aware, let's click the play button here. We have the ball bouncing from left to right, which is sort of fun. We've got a little bit of a game going here. But it's extremely boring, right? So, what do we need to do to make this more fun? Well, first of all, we need to maybe randomize at what angle the ball is going to fall. We need to actually give the ball some angles so that depending on where it hits in the paddle, it's going to deflect back at a sharper or a narrower angle, a narrower or wider angle. So if the ball, we're going to make it so that if the ball touches the very outside of the panel, the ball is going to go in a narrower angle, and if the ball, the further that the ball travels and collides with the center of the paddle, the wider the angle is going to get until we actually are going to be with a zero angle. So, in order to do that, we need to know a couple of things first. So I'm going to throw up a slide that I made, which is right here. Okay. So, yes. Tons of math, but believe me, this is actually very, very, very simple to understand. So, looking at the little slide I made here, okay. So our first question is what is a radian? Okay, so if you're looking at a circle and you draw from the center a radius, okay, a radius to the outside of the circle, and another radius, you have what's called an arc length between the two radius that you've drawn out in a circle. Which, of course, you've got your theta in the center of at the center point of the angle, which would be your angle. Okay, so your arc length is that little red line that I've drawn between the two radii. I don't know. Anyways, so that would be your arc length, and that length, if it's the same length as the actual radius from the center point to the edge of the circle, then that is equal to 1 radian. Okay? So then, if we've got 1 radian, if we go all the way around, okay, we'll have 2 pi radians, which is also equal to 6.28. Okay? So we've got a full revolution around a circle is 360 degrees. So then 2 pi, which is a full revolution around a circle in radians, would then equal 360 degrees in a circle if we used degrees instead of radians. So 2 pi for radians, 360 degrees. Same thing holds true if we went with a half a circle. So we've got 180 degrees. And that equals pi radians, so just 1 pi and 2 pi. And actually, you don't have to write radians after the pi symbol. It's kind of understood that pi is in radians when you're talking about the radians of a circle. So you're like 2 pi radians. It's the same thing. So we are going to do some conversions actually, because the methods, the functions that we're going to be using to help us with converting our angles to actual x and y coordinates in our game are going to be cosine and sine. And those functions, they actually require us to pass in radians instead of degrees. So one might need to know how to convert our degrees into radians if you want to, if you're looking at a circle and you can look at it and be like, okay, well, I can tell you exactly where 90 degrees is on that circle, or where 180 degrees is, or 270, or 360. But you may not be able to do the same thing with pi, or sorry, with radians as easily. You may not be able to look at a circle and say, okay, well, this right here is 1 radian, and that's going to give me exactly this angle that I want. No, it's a little tougher to understand or put visually. So to keep things simple, we're going to continue to work with degrees in our game, but we are going to convert those degrees into radians so that we can then pass those along to cosine and sine functions. So to convert degrees into radians, the only thing we have to do is we have to multiply pi by the number of degrees and then divide that by 180. Okay, and that'll give us our radians. And then in the same way, we can convert radians back into degrees if we do the opposite and multiply 180, multiply the radians by 180 and then divide by pi. So I've also made just a quick reference for you guys on the right hand side, so that you don't have to look at this big old sheet every time you want to look at this or figure this out. So I've just really quickly referenced, you've got 1 radian equals the arc length of r, you got 360 degrees equals 2 pi, 180 degrees equals pi, radians to degrees, x times 180 divided by pi, where x is actually equal to the radians, and degrees to radians, x times pi divided by 180, that's x is equal to the degrees. Of course, I kind of explain this in a non-technical math way. There are all kinds of other ways to explain this in a more professional sense, but I just kind of wanted to give you guys a really quick and dirty look at radians and degrees and how to convert between the two of them, because that's what we're going to be using. Let's get on with it. Let's open up our ball script, and to start with, we're going to create some variables. Okay? Let's create them. First, we're going to create a float, and that is going to be our bounce angle. And I'm going to explain what all these are for in just a minute. We're going to create another float, actually 2 more floats, Vx and Vy. And then just 1 more, and it'll also be a float, and it'll be our max angle. Okay, so what did I just do? I created 4 variables. We've got bounce angle, and bounce angle basically is going to be used to specify at what angle our ball should bounce from. Wherever wherever it will collide, we're going to at that point determine, okay, what's the bounce angle going to be from that location? And then we're going to assign that to that bounce angle variable. Vx and Vy will be our locations, our x and y grid coordinates, where our ball is going to travel to. And that is what our math functions, sine and cosine, are going to help us determine based on our bounce angle. So we're going to pass in an angle to those 2 functions, and it's going to spit out an x and a y, so that we don't have to do anything else. So very, very useful functions. The next thing we have is the max angle. And the max angle, we're actually going to set that equal to something. I'm going to set that equal to 45. And the max angle is going to be used for actually determining the maximum angle that we're going to allow our ball to travel in when it deflects from something, okay? So, with all these variables created, with that in mind, the first thing we're going to want to do is we're going to check what our move speed is. So, if our move speed is less than 0, we are going to actually set our move speed equal to, we're going to set our move speed equal to -1 times our move speed. So basically, if our move speed is less than 0, then we're dealing with a negative move speed. So we want to set our move speed to a positive move speed. So we just do that by multiplying by -1. Okay. So the next thing we're going to want to do is create a method. Yeah, I just scrolled all the way to the bottom. So our method is going to return a float, and we're going to call this method get random bounce angle, and we're going to create two parameters that you may or may not fill in. I'm going to call this min degrees, and I'm going to set it equal to something. We're going to set this equal to 160, and another one, and it's going to be max degrees, and we're going to set that equal to 260. Oops, and we're going to now, this basically just means that I've set these equal to something, means that we have these parameters, we can set these parameters, but if we don't set those parameters, then they're going to be equal to the values that I've defaulted them to. Okay? I'm going to show you that in just a minute. So first we're going to create a variable called min radians, and that's going to equal min degrees times mathf.pi divided by 180, and max radians will be max degrees times mathf.pi divided by 180. Okay, so and that's where those methods that are functions come in handy, where I showed you on the slide, where I showed you how to convert from degrees to radians, because our method, our sine and cosine method functions that are going to provide us with x and y coordinates, they want radians, they don't want degrees, so they want to work with radians, so we have to give them radians, and we give them radians by converting our degrees to radians. Then we're going to return, okay, random. We're going to use the random class. We're going to use a method called range, which takes in two parameters that are floats, a min and a max. So we're going to pass in min radians and max radians. Okay? And that is going to return our random bounce angle. So you could probably already guess the next thing I'm going to do is, in the start method, I'm going to start with our random bounce angle, and I'm going to set it equal to get random bounce angle. And, I was going to show you, when you open the parentheses, you'll see that it's telling you it takes two parameters, min degrees and max degrees, and it's telling you, okay, well, min degrees equals 160 and max degrees equals 260. You can set them here to whatever you want, but you can keep them as defaults if these are the values you want to use. Makes it quick and easy to make changes to those min and max angles if you want to test some other ones out. So, if you knew how to do this already, great. If you didn't, you learned something new. Otherwise, I mean, it's there, right? It's there for you. So, now that we've got the bounce angle, we can go ahead and set preliminary values for Vx and Vy. So Vx is going to equal our move speed times mathf.cosine, and we're going to pass in our bounce angle. Vy is going to equal our move speed times negative mathf dot sine, and we're going to pass in our bounce angle. So mathf.cosine and negative mathf.sine are used to return x and y coordinates from angles. Otherwise, we'd have to work with angles, and we'd have to calculate our x and y's. Mathf.cosine and sine do those for us, so we don't have to worry about it. Nice, right? Yes, I say so. So, the next thing we're going to need to do is in our move method. Because now that we've got a way to get a random bounce angle, we can start our ball off at a random angle to travel into, right? So, and if we're looking at this, and we're looking at this if statement here, basically saying, hey, if there are no collisions, we want to continuously move the ball. And we're just going to move the ball back and forth, back and forth, back and forth. Left to right, left to right, left to right. No angles whatsoever. we are going to change that. So, in order to change that, we actually have to set Vx equal to something, right? So Vx equals move speed times mathf dot cosine, and we're going to pass in the bounce angle. So now at every frame, we're setting Vx equal to our bounce angle times the move speed. For Vy, we need to actually check to see what our move speed is. So move speed, if it's less than 0, then Vy is going to equal move speed times negative mathf dot sine, passing into bounce angle. And otherwise, oh, there's my mistake. Otherwise, Vy will equal move speed times mathf dot sine, and we pass in the bouncing. Okay, so we calculate our Vy based on whether or not our move speed is negative or positive, because if we multiply a negative number by negative, wow, you know, it's Friday when I'm actually recording this video, and I have been working all week, and my brain is pretty much fried, so just bear with me. If the move speed is negative, and we multiply this negative move speed times the negative mathf dot sine, then we're not getting the value that we would expect to get from a negative mathf, or yeah, from a negative sine, basically. I don't know why I keep saying mathf. That's just the function that we're calling, a class that we're calling the sine function from the mathf class. Anyways, negative sine. So if we multiply negative move speed times negative sine, we are not going to get the expected y value that we want. So what we do instead is, if it's less than, we multiply it by the negative version, okay, the inverse. So if it is greater than, and we have a positive move speed, we multiply that by a positive sign, and we get back the y that we need. So with that in mind, we need to make a slight modification to our positioning here. So we're using our local transform. We're using our game objects transform, which is the ball. We're setting the local position. We're incrementing it, okay? So the way that we're going to change this is, we're still going to do vector 3. Actually, we're going to create a new vector 3. New vector 3. And we're going to multiply the ball direction for the x. This is just for the x. Ball direction dot x times Vx times time dot delta time. And then we're going to do Vy times time dot delta time. And then we're going to, for the z position, we're going to do 0. So just a quick note, the reason that we're multiplying Vx times ball direction dot x is because we need to actually move in, either a negative or a positive value along the x-axis, right? Vy, the ball isn't going to change direction depending on which paddle is being hit, right? So in the y direction, it's only going to change in the x direction. It's either going to go towards the left paddle or it's going to go towards the right paddle. So we have to multiply by the direction to get a proper Vx. So basically Vx is either going to be negative or positive. There you go. Okay, so now that we've got that, actually, so our ball's going to move, of course, unless, we are colliding, then we're going to want to do a couple of things. Because we want to know where on the paddle we're colliding. We want to be able to modify the angle that the ball is going to travel depending on where we collide. So we have to do the same thing here. We have to check if move speed is less than 0. Then we're going to go ahead and change move speed and set it equal to -1 times move speed. Alright, so it collided. So we're changing its direction, basically. So now we're going to create a variable, and we're going to call this relative intersect y. And that's going to equal the paddle player dot transform dot local position dot y minus transform dot local position dot y. And you're already asking yourself, what? This isn't right. This is not right. Why are we doing it this way? This is completely wrong. And it is wrong because this is only going to work for the player paddle. So we're going to create some booleans. So up at the top, we're going to do private bool collided with player. Oops. Collided with computer, collided with wall. Because the ball eventually will collide with the wall. Yes. So, in our collision detection, player paddle. Alright, so collided with player. Collided with computer. And we're going to do the collided with wall in a second. Let's just jump back down here real quick. So, if collided with player, it's true. We don't even have to type that. It's implied. Alright, if collided with player equals true, then the first thing we do is set collided with player equal to false. So we're basically resetting. Then we're going to do this. And we only have to do that for the y. Yes. Alright, so then we're going to create another float. And I'm going to explain all these lines of code to you in just a second. So it's going to be normalized relative intersection y. And that's going to equal the relative intersect y divided by player paddle height divided by 2. And then our bounce angle is going to equal normalized relative intersection y times max bounce angle times mathf dot degrees to radians. And yes, I cheated. Okay, so what are we doing? First, we're checking to see if collided with player is true. If it is, we say collided with player is false, because in the next frame it will no longer be colliding with the player. Then we're creating a relative intersect y. And what is a relative intersect y? We're creating this by taking the local position, the y, of the paddle, okay, where it's currently at, and we're subtracting the transform, or the local position, so the ball's local position, right? So we're subtracting the ball's local y from the paddle's local y. And that's going to give us our relative intersect y. The relative intersect y is going to be the position on the paddle itself and not the position in the actual game board. So we're getting a position on the paddle, right? Whether it's positive or negative. So we've got the center 0 here, and we've got our positive numbers and our negative numbers. So what this will do is this will give us an actual relative position on the paddle, okay? So then what we need to do is we need to actually get a normalized value for that, because we want to have either a negative or a positive one or a negative one. So a number between 1 and -1. Okay, that's going to be our normalized value. And we get that by just dividing our relative position by half of the paddle height. Okay? So then what we do is we assign, all right, to our bounce angle, we take our normalized value of y, we times that by our max angle, okay, times math_f.degrees to radians. So yes, that exists. There is a property that basically takes our degrees and converts them to radians if we just pass in the, if we just multiply that by the actual angle. So we're taking our normalized relative intersection y, which can be either a -1 or anywhere between -1 and +1, and we're multiplying that by our degrees, our radians in this case, because we're converting. So we're multiplying that by radians. So we're going to have a value of radians between a negative and a positive value that our angle, that our bounce angle is going to be at. Okay. So now we're going to check if or else if collided with computer. And we're just going to copy all of this, paste that in, collided with computer equals false. Here we're going to do paddle computer and computer paddle height, and that should be that. So now, if we save this, we should be able to go into Unity, press play, and our ball, yep, slight angle, and nope, didn't make it. So that's why we need to check to see if it's going to collide with the wall. Oh, well that didn't seem right. Neither did that. That just seemed wrong. What did I do wrong? What did I do? See, I thought that looked funny. Because, alright, remember all this time I spent explaining this? Because we want to take the negative sign value of the bounce angle to get the actual y coordinate. Well, we're checking to see if move speed is less than 0, which means that it would have to be a negative. So in order for it to be a negative, we would multiply this, and we would get these two cancel each other out, and we would get a positive sign value. Well, we don't want that. We want a negative sign value. So, greater than. There. Now, let's play. And that looks much better. And we're bouncing. And that one's probably too much. Yep. Okay, so, with that out of the way, what's left? We have to check the, we have to add some more collision detection. Lovely. Let's see where we're at here. Should be pretty simple, actually. All we need to do is check to see if the transform dot local position dot y is greater than or equal to top bounds. It's greater than top bounds. Did we not define top bounds and bottom bounds? We did not define a top bounds and a bottom bounds for the ball yet. Okay. So, you can take my word for this. Public top bounds is 5.875F, and those are floats. Bottom bounds equals negative 5.875F, and that's also a float. So top bounds back up here. Okay. So if it's greater than top bounds, our ball obviously collided with the top bounds, so we want to set its local position. Transform dot local position equals new vector 3. And we're not going to modify the x value, so it's transform dot local position dot x, and then we're going to set top bounds and transform dot local position dot z. And then we want to set collided with wall equals true. Yep, that's pretty much that. If transform dot local position dot y is less than top bottom bounds, we're going to set transform dot local position equals new vector 3 transform dot local position dot x bottom bounds transform dot local position dot z, and collided with wall equals true. And then in our move method, we've got if collided with player, else if collided with computer, else if collided with wall. We are going to say collided with wall equals false. And oh yeah, very simple. We basically just changed the bounce angle to the opposite bounce angle. So we're just setting it to a negative bounce angle because it's going to go the opposite way in both directions. So let's have a look here. Down. Whoa. So here's the thing. When I say trust me with numbers, that's not always accurate. So those are absolutely not our numbers. Let's throw our ball in here just to kind of check it out, see where we're at. So our numbers are more like 6.59, or sorry, 9.4, and of course negative 9.4. Okay. So back in the code, we'll do 9.4 and negative 9.4. Oops, I already had a negative. And let's play. And we go up, and what? Okay, wait. There's a thing. Something's not right. Okay, well, it definitely went where it was supposed to go that time. But it is definitely not deflecting, and I think I know why. Let's see here. We're not checking... Wait a minute. We're always checking collisions. Oh! Because we're not returning true. We have to actually return true because we've had a collision. Ah, now we're ponging. Take that, computer player. Look at that. That's perfect. Don't you guys love it when you make a game and it just works the way it's supposed to? It's really cool. Okay, guys, that pretty much covers it. That takes care of Pong. Well, not takes care of Pong. There are definitely more things to consider with this game, and we are going to cover all of them. So I think the next tutorial is going to be, if I can find my notes, so the next tutorial is going to be computer AI. So yeah, in the when we come back next week, we are going to add some artificial intelligence to our computer paddle so that our player can have an opponent that is worthy. Because right now we're kind of just playing against ourselves, which is a little boring because we know what move we're going to make, we know where to go to prepare for the next move, and that's just not a lot of fun. Although we can try to trick ourselves and do some trick moves and see if we're fast enough to catch our trick moves, but still. We want some competition, right? So that's why we're going to create an artificial intelligence computer paddle that is going to kick our ass. Maybe. We're good though, right? So, yeah, if you have any questions, feel free to leave comments down below. Yes, that's right. Thumbs up if you like the video, comments down below, and don't forget to subscribe. Also, don't forget to check out my Twitter and follow me on that and on Facebook. And if you subscribe, don't forget to click the little bell next to the subscribe button, because that's how you actually get email notifications when new videos come up. I've also started a Patreon. If you don't know what that is, I've got a link in my in the comment section or in the description section where you can go and check that out. Basically, you can help support the channel if you like the videos. Until next time, I will see you next week. I am the Weekly Coder.